A student investigates the reaction between ethanoic acid and methanol in the presence of an acid catalyst. The equation is shown below. Part A. The student carries out an experiment to determine the order of reaction with respect to ethanoic acid. The student uses a large excess of methanol. The temperature is kept constant throughout the experiment. The student takes a sample from the mixture every 20 minutes and then determines the concentration of ethanoic acid in each sample. From the experimental results, the student plots the graph below. Part 1. Explain why the student uses a large excess of methanol in this experiment. So the reason that the student is using such a large excess of methanol is so that its concentration is constant. So to get the mark for this question, you can write this statement. They will also accept saying that zero order with respect to methanol, or to ensure equilibrium is far to the right. So one of these three statements will get the mark for this question. Part 2. Use the half-life of this reaction to show that the reaction is first order with respect to ethanoic acid. Show your working on the graph and below. For this question, we need to go back to looking at the graph, and we're going to work out half-lives. So the first thing to do when working out half-lives is to draw a line of best fit. So this line has to go through as many points as possible, and we're going to curve slightly towards the end of this line of best fit. So then we need to work out half-lives. So if we start with the concentration of 4, half of this is 2. So then we read off on the graph where it intersects with this line of best fit and read off the minutes. So for 4, that's going to be this point here. Reading this off, we get 36 minutes. Then looking at number 2, so that's going to intersect here at 140 minutes. So we do 140 minus 36, which equals 104 minutes as our first half-life. But we need to do more than one. So if we do 5 and then 2.5, which would be here, reading off from 5 we have 0, and then 2.5, reading that off here, this is going to be 104. So our second half-life is 104 minutes. So if we go back to part 2, so we have 2 half-lives, and they're going to equal 104 minutes. So the fact that they're constant, well, that's going to indicate that it's a first order reaction. So if constant half-lives, so it's first order. To get the marks for this question, you get a mark for working out the half-lives, so 104 minutes, but it can be in the range of 102 minutes to 110 minutes. And then you get your second mark for saying that constant half-lives mean that it's first order. Part 3. Determine the initial rate of reaction. There are 2 methods to working out initial rate of reaction. The first one involves using the graph. So if we go back and look at the graph, I've drawn a tangent at the time equals 0, and then we're going to work out the gradient of the tangent. So if we use 2 and 4 again as our y values, reading off from 4, that's this green line here, and that's going to be 30 minutes. And then looking at 2 and reading off from 2, that's here, and that's going to be 92 minutes. So if we work out our gradient, so the units on the y-axis are times 10 to the negative 3 moles per decimeter cubed. So our numerator is going to be 4 minus 2 times 10 to the negative 3, then divide by 92 minus 30, which equals 3.23 times 10 to the negative 5 moles per decimeter cubed per minute, which we can write on the answer line, 3.23 times 10 to the negative 5. Now looking at the second way we could have answered this question. So the second way to do this is using the equation of K equals ln2 divided by the half-life. So the half-life is 104 minutes, which we've worked out. So that's ln2 divided by 104, which equals 6.66 times 10 to the negative 3 minutes to the minus 1. Then we multiply by the initial concentration. So looking at the graph, that's going to be 5 times 10 to the negative 3. So if we do 6.66 times 10 to the negative 3 multiplied by 5 times 10 to the negative 3, we get 3.33 times 10 to the negative 5 moles per decimeter cubed per minute. So we can see that both of these methods get a relatively similar answer, and the mark scheme will accept any value in the range of 2.9 times 10 to the negative 5 to 4 times 10 to the negative 5. So there's quite a big range, and both of these values are in that range, so it doesn't matter which method you use as long as you do it correctly. So in method 1, you get your 2 marks from 1, drawing the tangent, and 2, working out the gradient of the tangent. In method 2, you get your marks for working out k, and then multiplying by 5 times 10 to the negative 3. Part B. The student carries out a second experiment to determine the value of Kc for this reaction. The student mixes 9.6 grams of methanol with 12.0 grams of ethanoic acid and adds the acid catalyst. When the mixture reaches equilibrium, 0.030 moles of ethanoic acid remains. Calculate Kc for this equilibrium. The first thing to do with this question is highlight the key piece of information. So that's the mass of methanol and the mass of ethanoic acid, that the equilibrium moles of ethanoic acid is 0.03 moles, and that we want to calculate Kc for this equilibrium. So the first equation triangle we're going to use is one where we've got mass at the top, and mass is equal to moles times the relative formula mass. So we're going to calculate the moles here, where we've got 9.6, we're going to divide by 12 plus 3 plus 16 plus 1, which is the relative formula mass of methanol. And that equals 32, and it's going to equal 0.3 moles when you divide. Then we're going to work out the moles of ethanoic acid, which is 12 divided by 12 plus 3 plus 12 plus 16 times 2 plus 1. So when we divide this, we get 0.2 moles. So then we're going to do what's called an ice equation, where you have each of your species and then you have the initial moles, change in moles, and equilibrium moles. So if we start by writing out our species, we have CH3OH, we have CH3COOH, we have CH3COOCH3, and we have water. So this is a standard esterification, where you've got an alcohol and a carboxylic acid producing an ester and water. So next we're going to look at their initial moles, their change in moles and their equilibrium moles. So initially methanol is going to have 0.3 moles and ethanoic acid has 0.2, whereas our products of the equilibrium will start with 0. So we're told that the reaction mixture reaches equilibrium and we have 0.03 moles of ethanoic acid. So we can write this in our table, 0.03. So that's a change in moles of minus 0.17. So that's going to be the same because it's the same molar ratio, but where we have our products, we're going to add 0.17 rather than subtracting. So we have 0.17 of our ester, 0.17 of our water, and we have 0.13 moles of our methanol left. Then we write an expression for Kc. So Kc is equal to the concentration of our ester, so CH3COOCH3, multiplied by the concentration of water, divided by the concentration of methanol, then multiplied by the concentration of ethanoic acid, so CH3COOH. So we don't have the volume, but that doesn't matter because the volumes will cancel out. So if we write this expression for Kc and use volume as V, we would have 0.17 divided by V in square brackets multiplied by 0.17 divided by V in square brackets divided by 0.13 divided by V in square brackets times by 0.03 divided by V. So all the volumes here are going to cancel out. So it doesn't matter that we haven't got a volume to work out concentration. So if we ignore volume and we just type in the numbers in this expression, we get 7.4 as our value for Kc, which we can write on the answer line provided. To get the 4 marks for this question, you get a mark for working out initial moles, you get 2 marks for working out equilibrium moles, and then you get 1 mark for using your Kc expression to work out Kc.